The 2025 Nobel Prize in Chemistry honors three remarkable scientists: Susumu Kitagawa from Japan, Richard Robson from Australia, and Omar Yaghi from the United States. Their groundbreaking discovery of metal organic frameworks has transformed materials science, creating molecular structures that can trap carbon dioxide, store hydrogen, and even collect water from desert air. This innovation opens the door to cleaner energy and a more sustainable planet. Awarded by the Royal Swedish Academy of Sciences, the Nobel Prize celebrates achievements that redefine human progress.
Conference where we will present this year's Nobel Prize in Chemistry. My name is Hans Ellegren. I'm Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Heiner Rinke, Chair of the Nobel Committee for Chemistry. And to my left, Professor Olof Ramström, member of the Nobel Committee for Chemistry and one of the experts in this field. Årets pris handlar om att skapa nya rum för kemi. This year's prize is about creating new rooms for chemistry. Susumu Kitagawa, Kyoto University, Japan. Richard Robson, University of Melbourne, Australia. Och Omar Yaghi, University of California, Berkeley, USA. För utveckling av metallorganiska ramverk. Royal Swedish Academy of Sciences has decided to award the 2025 Nobel Prize in Chemistry to Susumu Kitagawa, Kyoto University, Japan, Richard Robson, University of Melbourne, Australia, and Omar Yaghi, University of California, Berkeley, USA, for the development of metal organic frameworks. Professor Heiner Rinke will now give us a short summary in English. Please.
Yeah, ladies and gentlemen, we have a great prize for you today. Imagine that the tools of chemistry could be used to create entirely new materials with unheard of properties. For example, imagine we could make solid materials full of tiny spaces in which gas molecules can feel at home and with chemical properties that can be adjusted to the specific needs and wishes of different molecules. One could then imagine to create materials that can separate carbon dioxide from air or from industry exhaust pipes. Or that could be used to separate toxic molecules from wastewater. One could imagine making materials that can harvest water molecules from dry air and make potable water in a desert. Or materials that have catalytic properties on their inside, so that toxic gases could be absorbed and then transformed into unharmful substances. This year's laureates have achieved just that. They have found ways to create materials, entirely novel materials, with large cavities on their inside, which can be seen almost like rooms in a hotel, so that gas molecules can enter and also exit again from the same material. A small amount of such material can be almost like Hermione's handbag in Harry Potter. It can store huge amounts of gas in a tiny volume. This type of materials, called metal organic frameworks, can be created with almost unlimited variations, creating unending possibilities for the greatest benefit to humankind. Thank you.
And here you can see a typical construction framework. It happens to be made from wood, where the wooden boards or planks are joined together, assembled, probably using metal nails or screws. And of course this makes up the skeleton of this construction or this future house, but you can actually see hinted here the many rooms inside this framework. So we have the metal ions as nodes, and then we have the organic molecules as linkers.
And once you have identified those and mixing them together, they will then find themselves and arrange themselves in a type of self-assembly process into an ordered framework, a metal organic. Very difficult challenge for many, many years. And although we actually knew about structures that look like this, how to actually predictably being able to make them was very elusive. But let's go back to the late 1980s. At that time, Richard Robson, he reasoned that it would indeed be possible to build such frameworks predictably by taking metal ions and molecular organic linkers. He was inspired by the structure of diamonds, as you can see here. Each carbon atom in diamonds are surrounded by 4 other carbon atoms in a pyramidal or tetrahedral orientation or shape, and as you can see here in red. So Richard Robson reasoned that if you take a metal ion, in this case copper 1,
has a so-called nitride, and the copper ion and the nitride groups, they can find each other and form bonds, and that will in principle lead to a structure that will be similar to the structure of diamonds. Well, contrary to the general expectation at that time, in the late 80s, this actually worked really, really well. Framework structure, as you can see here. Now, in contrast to the structure of diamonds, where the carbon atoms are very, very tightly packed, this framework, however, contained cavities or holes. And as you can see, it's relatively large cavities or holes. And by, we call them inclusions, compounds, in this case solvent molecules, and also negatively charged ions, what we call counter-ions. Once having showed this work, this demonstrated that this is indeed possible a few years, and Susumu Kitagawa, he managed to demonstrate that gas absorption is